So Gary and me, we decided to talk about normal linear models, and specifically we're going to talk about the 5 main assumptions of linear regression. All right. First of all, it's important to say that we can never prove these assumptions. We can merely develop devices to check for them and see if we can use linear regression for a specific case. Mainly we do that by using plots. All right. The first assumption is one of normality. All right. This says that our error components have to be normally distributed. And this is for all i's basically. So I equals 1, 2, n. Right, that's the first assumption. Second assumption is the one of homoscedasticity. And this assumption says that our error components have to have the same variance, all of them. Therefore, we can show it by for all i's, and I is also between 1 and n. The third assumption is the assumption of independence of error components. That means that all the errors have to be mutually independent. Therefore, EI is independent of EJ. And it's important to say that I does not equal J, and this holds for all I J equals 1 to n. The third assumption is the assumption of the fourth assumption is the assumption of linearity. And this says that the expected value of our response has to be a linear combination of all the covariates and parameters in our model. We can just show this by expectation of yi equals beta 1 assuming we have p covariates parameters in the model. And then the fifth assumption is one of collinearity. We don't want any linear relationship between each individual covariates. How do we check that? We can check it by plotting each covariate against each other, and if there's a linear relationship, we should further investigate that and potentially avoid a covariate from the model. Gary will talk about that more. All right. So there are 3 ways how to check for these assumptions. 3 kind of most common ways. First of all, you can plot residuals against covariates. Second is plotting residuals against fitted values. And thirdly, you can plot residuals against some kind of time variable. This could help you identify any the independence assumption, basically. Because if there is a relationship between time and your residuals, this indicates that there is not independence between your error components. And Gary will show an example of that. It's very important to say that residuals are estimates of our error components, but residuals don't have equal variances. Each residual has a different variance depending on the head matrix. I'll just show that. Variance of So this is the variance of the ith residual is the standard deviation times 1 minus the ith value in the H matrix. Therefore, it changes for each I. And in addition to that, the residuals are correlated. So covariance between residual I and residual J is minus sigma squared H I J. Alright. In order to avoid that, we will use standardized residuals. And we do that by dividing our residuals by its variance. This allows us to have a random variable that has 0 expected value and a constant variance of 1. However, it's important to realize that there is still a correlation between standardized residuals, but normally it shouldn't cause any problems and issues looking at plots. Now over to Gary, and he will show you some examples.